Air has weight. It presses down on the ground and on the wings of anything trying to leave it. But in some places, on some afternoons, that air can become so light that it stops holding aircraft up at all. You cannot see it happen. You cannot feel it standing still on the ramp. The aircraft can. The sun heats the concrete. The concrete heats the layer of air sitting directly on it. That warmed air spreads apart, thins out, and lifts away from the surface in a shimmering sheet. And a wing moving through that sheet finds less of it to push against. At first, this might just seem like a bad day for comfort. A hot ramp, a late departure. Something a passenger complains about at the gate and forgets by the next morning. It is not that. It is a hard limit printed in the flight manual of every aircraft ever certified, and when the outside air crosses it, the aircraft does not leave. Not because someone chose to be careful, because the air stopped cooperating. So what actually happens to a wing when the air around it thins out? And why does the same afternoon that grounds one aircraft leave the one parked beside it completely unaffected? You have walked across a parking lot in high summer and watched the air above the asphalt wobble and bend the cars behind it. You were looking straight at the problem. You were simply not looking at it from a cockpit. Most people think of air as empty space. It is not. It is a fluid. And like every fluid, it has a density, and that density changes with temperature and with pressure. Cold air is packed tightly. Warm air is loose. A wing does not care how many degrees the thermometer reads. It cares how many molecules of air it can shove downward in 1 second, because shoving air downward is the entire trick by which anything heavier than air stays up. To understand why aircraft stop flying on the hottest days, you have to stop looking at the temperature and start looking at what the temperature does to the spacing between molecules. There is a reference point for this. The International Civil Aviation Organization publishes a model called the Standard Atmosphere, issued as Document 7488, and the United States maintains its own version last revised in 1976. Both describe the same imaginary day. At sea level, the temperature is 59 degrees Fahrenheit, or 15 degrees Celsius, and the pressure is 29.92 inches of mercury. Every performance chart in every flight manual is built on that imaginary day, and then corrected away from it. The correction has a name. Engineers call it density altitude, and it is the single most useful idea in this entire subject. Density altitude is the altitude at which the air would be this thin on a standard day. It is not where the aircraft is. It is where the air thinks the aircraft is. An airport can sit a few hundred feet above the sea and, on a hot afternoon, present its runway to an aircraft as though that runway had been lifted several thousand feet into the sky. Nothing physical moved. The pavement is where it always was. But the wing, the propeller, and the engine compressor are all working in air that belongs somewhere much higher up. Phoenix Sky Harbor International Airport is where this stops being an abstraction. The field sits at roughly 1,118 feet above sea level, which is low. Its north runway, designated 8 and 26, is 11,490 feet long and 150 feet wide. The center runway is 10,300 feet. The south runway is 7,800 feet. By any ordinary measure, that is a generous amount of pavement. And then the desert does what the desert does. What follows is that arithmetic being taken apart, one piece at a time. This channel exists to take apart the systems that hold enormous cities together. So if that is what you came for, subscribe and stay with it. In 2023, the National Weather Service recorded 31 consecutive days in Phoenix at or above 110 degrees Fahrenheit, a streak that did not break until the first day of August. In 2024, the city ran 113 straight days at or above 100 degrees. The all-time record for the city, 122 degrees, was set on the 26th of June, 1990, and it has stood since. None of those numbers describe a freak event. They describe a season, arriving on schedule, every year. On the 20th of June 2017, the forecast for Phoenix reached 120 degrees. American Airlines canceled more than 40 American Eagle regional flights. Across the Monday and the Tuesday, the count reported at the time was around 50. The aircraft involved were Bombardier CRJ regional jets, and the reason given was direct and unglamorous. The maximum operating temperature written into the CRJ documentation is 118 degrees. The air outside was going past it. The aircraft parked at the next gate did not move either, but for a different reason. Larger airframes are certified to higher outside air temperatures. Boeing aircraft are generally cleared to 126 degrees and Airbus aircraft to 127 degrees. That gap of 8 or 9 degrees decided which flights left Phoenix that afternoon and which ones did not. Brett Jensen, a Boeing spokesman, put the mechanism in one sentence at the time. Hotter air is less dense, which means there is less air beneath the wings for lifting the aircraft and less air to flow through the jet engines. 2 losses, not 1. That second half matters more than most people realize. Here is the part that is easy to miss. A jet engine is an air pump. It takes in a mass of air, adds fuel, burns it, and throws the result backwards. Thrust is a function of mass flow. When the air thins, the same compressor spinning at the same speed pulls in less mass every second and produces less thrust. So the wing needs more speed to generate the same lift, and at exactly that moment, the engine has become less able to provide the speed. That is the trap. The demand goes up, and the supply goes down, in the same air, at the same instant. And it explains the detail that looks unfair at first hearing, which is why the small jet was the one grounded. A regional jet carries less wing area and less installed thrust than a wide-body, and it was certified against a set of conditions its designers considered representative of the routes it was built for. Short sectors, regional airfields, not a desert basin in the last week of June. The larger aircraft was not built tougher in some general sense. It was simply certified against a hotter day, because the routes it was sold for included hotter days, and that decision was made in a design office long before either aircraft ever saw Arizona. There is a second, colder way to look at that 8-degree gap between 118 and 126. It is not a safety margin. It is the edge of what a manufacturer was willing to test, document, and stand behind. Beyond a certified limit, an aircraft does not become dangerous in some sudden way. It becomes unknown, and an operator is not permitted to fly into unknown. Underneath all of this sits a second hidden system that passengers never think about, which is the arithmetic of runway length. The Federal Aviation Administration publishes design guidance for this in Advisory Circular 150-5325-4B, and the certification rules for transport category aircraft live in Title 14 of the Code of Federal Regulations, Part 25. Between them, they define something called the balanced field length. It is the runway distance at which 2 numbers become equal, the distance needed to accelerate, lose an engine at the worst possible moment, and still stop, and the distance needed to accelerate, lose that engine, and still go. A dispatcher is solving for that number before every departure. Not approximately, exactly, with the day's temperature, the day's pressure, the aircraft's weight, the runway slope, and the wind all entered. The Federal Aviation Administration's own pamphlet on this subject, catalogued as FAA P8740-2, carries a worked example that is worth hearing in full because the size of it surprises people. Take an aircraft that needs 1,000 feet of runway to get airborne and climb to 50 feet on a standard sea level day. Put that same aircraft at a pressure altitude of 6,000 feet with the outside air at 100 degrees Fahrenheit. The takeoff distance becomes 3,300 feet. The rate of climb falls from 500 feet per minute to 120 feet per minute, 3 1/3 times the runway, a quarter of the climb. Same aircraft, same pilot, same engines, different air. Now put an obstacle at the end of that runway, and the whole question changes character. On a cool morning, the departure path is a formality. On a hot afternoon, it is a calculation with very little slack in it, and the calculation only matters at all in the one situation nobody plans for, which is the failure of an engine somewhere between the decision speed and the moment the wheels come up. This is why the limit exists in the first place. Not because a CRJ falls apart at 119 degrees. Because at some temperature, the guaranteed performance the manufacturer certified can no longer be guaranteed, and past that line, the manufacturer stops promising and the operator stops departing. So how do the people responsible actually measure any of this? They do not measure density altitude directly. Nobody carries an instrument that reads it. It is computed from three things that can be measured: the field elevation, the altimeter setting, and the outside air temperature at the runway threshold, not at the terminal, not at the weather station on the far side of the field. And that last distinction is where the operational questions start piling up. The official reading comes from an automated surface observing station sited to national standards, in a ventilated shield, roughly 5 feet above a grass or gravel plot, chosen to be representative of the field. That sighting is deliberate, and it is correct, because a thermometer bolted to a black concrete apron would read a temperature no aircraft actually flies in. But it also means the number in the paperwork is a number from one particular patch of ground, and the aircraft is somewhere else on the airfield, over a different surface, at a different moment. Which thermometer counts when the ramp surface is 30 degrees hotter than the air 3 feet above it? What happens when the temperature is still climbing during the pushback and the taxi, so the number used for the calculation is already stale by the time the aircraft lines up? Who decides whether to wait 2 hours for the evening cool, or offload cargo now, or offload passengers, or refuel to a lower weight and add a stop that was not in the schedule? None of those questions have a single clean answer, and all of them get answered anyway, several times an afternoon, in a room with a clock running. I looked for a published record of how often Phoenix Sky Harbor departures have been weight restricted purely by temperature over the last decade, broken down by aircraft type. I could not find one in the public domain. If a dataset like that exists, and you know where it lives, put the link in the comments and I will pin it. It also helps to know that Phoenix is not the hard case. It is the visible one. Denver International Airport sits above 5,400 feet and lives with a permanent density altitude penalty that has nothing to do with heat, which is why its longest runway runs to 16,000 feet. That runway is a physical answer to a problem in air density, poured in concrete. Elsewhere, the numbers get stranger still. Kuwait recorded around 129 degrees in 2016. Death Valley, California, holds the highest reliably discussed reading anywhere, 134 degrees, from 1913. Airfields in those conditions are not edge cases to aviation engineers. They are a design category, and they get their own charts. Wind makes it more complicated, not less. A headwind is free performance, because the wing only cares about the air moving over it, not the ground moving under it. 10 knots straight down the runway can hand back a meaningful slice of what the heat took away. But desert afternoons rarely offer a steady headwind. They offer thermals, dust, shifting surface winds, and occasional outflow from distant storms. And a tailwind, even a light one, does the opposite. It lengthens the takeoff roll at precisely the moment there is nothing spare. So what do engineers and operators actually do about it? There are 4 levers, and every one of them costs something. The first is to fly at a different hour. This is why heavy departures out of hot airfields cluster into the early morning and the late evening. It is the cheapest fix in physics and the most expensive fix in scheduling, because it collides with connection banks, crew duty limits, and airport curfews. The second is to make the aircraft lighter. Less fuel, fewer bags, fewer passengers. A load planner can trade payload for performance at a known exchange rate, and airlines do exactly that, quietly, far more often than the traveling public notices. The third is to change the aircraft. Boeing sells what it calls a hot and high package, which provides slightly more thrust and slightly larger control surfaces on the wing. Fleets that serve hot airfields get specified differently from the ones that do not, years before the hot afternoon arrives. The fourth is to change the airfield, build the runway longer. Sky Harbor's 11,490 feet is not an accident of geography. Runway length at a hot, high, or obstacle-constrained airport is bought in advance, with concrete, against afternoons that have not happened yet. There is a fifth lever that is not really a lever, and it is worth naming because it is the one the public sees. Cancel. When the temperature crosses a certified limit, there is no clever trade left. No amount of offloading brings a CRJ back under 118 degrees, because the limit is not about weight at all. It is about the outside air, and the outside air is not negotiable. That is the difference between a weight-restricted departure and a grounded one, and the two get reported in the same sentence by people who do not know there is a difference. Something else worth sitting with. 3 of those 4 levers are decided years or decades before the hot afternoon. The fleet was specified. The runway was poured. The schedule was built. By the time the temperature is actually climbing at the threshold, the only lever still moving is the load planners, and it is the smallest one. Here is what a passenger sees on a day like that. They see a delay board. They see an aircraft sitting at a gate with the door closed. They see a gate agent with no useful information and a departure time that keeps sliding by 20 minutes at a stretch. Nothing about the scene suggests physics. Here is what the dispatcher sees. A temperature curve climbing through the afternoon, a performance table with a hard edge printed on it, a runway of fixed length that is not going to grow, a weight that has to come down, or a clock that has to run out, and a captain on the other end of the radio waiting for a number. What follows is a hypothetical engineering stress test. It is not a description or a prediction of an actual event at any specific airport or with any specific operator. Imagine a hot airfield in the last week of June. The surface temperature is climbing past the point where the smallest regional aircraft in the fleet has already stopped departing. The wind is light and, for the last 40 minutes, has been coming from behind the departure runway rather than in front of it. The longest of the 3 runways is closed for a pavement repair that was scheduled in the winter when nobody was thinking about June. That leaves the shortest. Now add the ordinary things. It is a peak travel week and the aircraft are full. A thunderstorm cell 200 miles east has pushed a wave of diversions into the airfield, so the ramp is congested and taxi times have doubled, which means the temperature at the threshold is higher than the temperature used when the paperwork was printed. One aircraft in the sequence has an auxiliary power unit that is inoperative under a deferral, so its air conditioning packs are drawing from the engines, which costs thrust at exactly the wrong moment. What is the last aircraft in that queue actually cleared to carry? Who tells 200 people they are not all leaving? Does the crew accept the shortest runway with a tailwind component and a reduced margin, or hold for the long runway to reopen and run into a duty time limit? How much of that decision is written down in advance, and how much of it is a person making a judgment with a queue behind them? The answer is that almost all of it is written down in advance. That is what the performance tables are. Every one of those questions was anticipated by somebody years earlier, sitting with a certification requirement and a wind component chart, and the answer was reduced to a number a dispatcher can read off in under a minute. The system works, not because the afternoon is predictable, but because the arithmetic was done long before the afternoon arrived, which reverses the way this whole thing looks from the terminal window. A summer afternoon at a hot airport, with flights leaving on time and nothing visibly wrong, is not a normal day that requires no effort. It is the output of a very large amount of anticipatory work, certification limits set by manufacturers, runway lengths bought decades in advance, fleet decisions made years before delivery, and a dispatcher recalculating the same problem every hour as the temperature moves. The absence of drama is the product. A few things should be said plainly. Everything described here is a general physical principle, and the degree to which it affects any particular airport, aircraft, or flight varies enormously with elevation, runway length, obstacles, weight, and equipment. Nothing in this video asserts that any specific airport or airline is currently experiencing a problem. The scenario in the stress test section is a hypothetical illustration built to show how several ordinary constraints can interact, and it is not a report of any real event. Footage used here is stock material for illustration and is not evidence of a defect anywhere. This is educational content, and it is not a substitute for professional aviation, engineering, or operational advice. If you want to understand the hidden systems that keep enormous cities and their airports functioning, make sure to subscribe to the channel. And one question for the comments. Have you ever been on a flight that offloaded bags, fuel, or passengers before departure on a hot day? And did anyone actually tell you why? Tell us which airport in the comments below.